Okay.
Yes.
Let me work on sharing for a second.
Excuse me. So, okay, I think most people are here, so we can begin.
Okay, cool. If I do this, do you guys see the
Yeah.
slides as the whole window? Okay, cool.
We can see. Awesome. All right. So, good evening, everyone, and welcome to the session. Today, we have prepared an exciting talk on the cutting-edge world of computer graphics, and we are very privileged today to welcome an exceptional speaker, someone whose contributions to the field have not only advanced our understanding, but also redefined the boundaries of what's possible in visual computing. So Dr. Steve Marschner is a professor of computer science at Cornell University, where he is conducting research in computer graphics and vision, centered around how optics and mechanics determine the appearance of materials. He obtained his bachelor's from Brown University in 1993 and his PhD from Cornell in 1998. In 2010 and 11, he was a visiting professor at ETH Zurich, and in 2023 to 24, he was a visiting research scientist at NVIDIA Research. He is an ACM Fellow, a recipient of the SIGGRAPH Computer Graphics Achievement Award in 2015, and a co-recipient of a 2023 Technical Academy Award. Just as my introduction, Dr. Marschner has worked on some of the most influential and amazing computer graphics tools that have pushed the boundaries of computer graphics. One of them is the development of the subsurface scattering model, a technique that revolutionized how translucent materials such as skin and marble is rendered. This technology actually played a huge part in the in the creation of lifelike digital characters such as Gollum in The Lord of the Rings and Dobby in Harry Potter, which are, I have to say, some of my favorite characters in movie industry because of just how they're designed and how they look. In addition to that, he's also worked on hair modeling and rendering, which I could say is personally one of the most incredible works in computer graphics. Because as a 3D artist and a gamer myself, I have noticed how hair has gotten from the stage where it's unrealistic and blocky to very immersive and super detailed. And Marschner hair, as they call it, had a big impact in this industry. So he is also a co-author of a computer graphics textbook called Fundamentals of Computer Graphics, and many introductory computer graphic courses are used from that book. And as a professor, Dr. Marschner has not only contributed to the body of knowledge in computer graphics, but also inspired countless students to explore and innovate in this dynamic field. So today, Dr. Marschner will share his insights in his topic, which I will keep a surprise for him. And with no more time wasted in introduction, I will give the stage to Dr. Steve Marschner.
Thank you for that really nice introduction. And it's an honor to get a chance to talk to this group. As Joshua pointed out, a lot of my research has been on visual appearance and sort of modeling why things look the way they look and how to represent them realistically. So I want to just give you a tour through a few different projects and with sort of a focus on ones that have had an impact in the film industry. Get my keyboard focus in the right place. So I just want to start out with a little bit about how we usually think about materials in computer graphics. How do you get stuff to look like it's made out of the right kind of physical material? And if you open up your physics book and flip to the page that talks about interaction of light with matter, you'll find some discussion that says like, oh, okay, well, if there's an interface that separates, say, metal from air or glass from air, you can write down some simple equations that describe how much light reflects and how much light transmits. And when you have a smooth interface, you get a mirror-like or glass-like behavior. And with these very old equations, you can make really realistic renderings of things that fit this model. So like glass and water, um, or things like metal, pure metals that have smooth surfaces. Um, Here are some more dielectrics. And this model works really well. It makes really realistic images. The problem is that the world doesn't all look like this. Not everything is these shiny, smooth surfaces. And this is not so much because those classic old equations are wrong. It's just that the structure of the material is not this very smooth surface. So like here's a metal that doesn't look like a shiny mirror, and that's just because it's got a rough surface. So the features on the surface scatter light to a range of directions. Or this chalk here is basically the same as glass. It's just ground up into really small pieces. And it makes it look completely different. It looks like this diffuse white material because light interacts with this like big pile of grains and it bounces around in the subsurface and kind of forgets where it's come from so that it comes out very uniformly in many directions. Um, and we have classic models in graphics that are really good for modeling these kinds of materials. So rough conductors are handled pretty well by microfacet models. Rough dielectric surfaces are handled pretty well by generalizations of those same kinds of models. And then the most widely used model for subsurface scattering, like in that chalk, is the diffuse model that just says the light goes out equally in all directions. So these are kind of the basic pieces of the classic toolbox that people might call physics-based shading in computer graphics, that you have shiny smooth surfaces, and then you have shiny rough surfaces, and then you have Lambertian diffuse surfaces. And the fundamental assumption here is that light reflection happens at surfaces. So the part of this story that I want to sort of carry forward is the idea that it's the small scale structure of materials that determines what they look like. But if you look at a wider range of materials, you can find all kinds of things that where scattering is not really happening at a surface. So here's just a pile of salt, and it basically looks like this white kind of translucent material. If you look at the individual grains, they look kind of glass-like and transparent, and it's really like the mass of stuff that gives rise to this white appearance. Um, Hair is another example of something that's not so surface-like. It's like a bunch of fibers floating in space, and the arrangement could be very different for different kinds of hair. The amount of pigment could be very different for different kinds of hair, but basically the structure is always about the same, and it's the arrangement of these hairs that gives rise to the overall appearance. Wood is something I think is really fun to think about, but which I won't have time to talk about. But it's kind of similar to hair actually in being like a like packed together mass of fibers. Um, and cloth is another material that's very important for realistic graphics with characters. Um, and cloth is really, again, just a whole bunch of fibers that are arranged in space. And it's not so much the properties of these fibers, although they're important in the appearance, but it's really the arrangement of the fibers geometrically that gives rise to the appearance. So I'm going to try to go through three projects that kind of cover some of these different materials. We'll see if I make it through on time here. So I want to start with some pretty old stuff, which is about translucent materials. Um, and I guess I titled this Reflection from Skin and Other Materials, but it's kind of interesting that the importance of this work for skin was actually a surprise to us after we had almost finished the project. Um, so this is work that I did during a postdoc at Stanford many years ago. Um, and if you render a lot of materials that are you sort of think of as diffuse-ish materials. So milk is one example, or skin is another example. And you render them with a diffuse shader, they'd really look wrong. Like this glass looks like it's full of white paint, and this face really looks like it's cast out of plaster or something like that. It's something that's well, I guess we didn't understand this at the time, but the problem is that they're too opaque. Um, and we were interested in this question of translucency and how to measure and model it. Um, and one of the things that we did is make a bunch of measurements in the lab of marble. So this was At the time, another project that was going on in the lab was the digital Michelangelo project that involved scanning a whole lot of plaster statue, or sorry, a whole lot of marble statues. Um, and the people who were doing laser scanning had run into problems that were caused by the laser sort of the light bleeding through the marble and coming out, not right where it lands. And if you're laser scanning, this causes errors in the scans. So we wanted to model this, kind of motivated by that. And so we did an experiment of taking a little block of marble and focusing a little tiny dot of light on it through a camera lens. Um, and if you look at this in the light, you see like a little dot. But actually the dot is already much bigger, like so this is a 40 millimeter cube, and the pinpoint of light is actually only about 1/10 of a millimeter wide, but it's kind of spread out into a spot. But if you turn out the lights in the room, then you can see that light escapes from the entire surface of this cube. It's actually very translucent. It's just that the light gets pretty dim after it goes a long way. Um, and the marble, interestingly, the light going through marble gets sort of reddish orange as it goes for a long way, even though the material is bright white when you look at it. So the idea that we had was that if you could just figure out a simple rule that says, as a function of distance from where you went in, how much light is going to come out, then you could make a rendering of a material like this without completely breaking the bank on doing lots of path tracing and stuff, which was way too expensive at the time. And if you look at an image like this, so this is a sort of a high dynamic range photograph that was taken in a calibrated way, so you can look at pixels of this as sort of measurements of radiance leaving the surface. And for a lot of different materials, you'll always see a shape that looks kind of like this if you plot that light. So this is the light escaping the surface as a function of the distance from where the small point of light went in. And there's actually Pat Hanrahan pointing out some biology papers to us over and over again until we finally actually went and read them and understood them. That caused us to find the models that already existed that were good for modeling this kind of thing. And the idea is to build on the physics of volume scattering. So if you have light scattering in a volume, so you like send a laser beam in there, say, one of the things that happens is as it travels through the volume, it dies out. So it's called extinction. Some of the light that disappears from that beam is actually not getting absorbed, it's just getting scattered into other directions. So there's scattering in a medium. And then when there's scattering, the scattered light can scatter again and again. And if the material is pretty white, like it's not absorbing a lot, then it gives you long scattering paths and the light gets really far. And people have thought about multiple scattering a lot in a lot of contexts. So the atmosphere is one of them. So modeling of light and as it moves through clouds. And you can use the mathematical model of diffusion to describe multiple scattering if there's lots and lots of scattering events. And so based on that, people have made models for this kind of situation called a half space illumination problem, where you send light in one point, and then you ask, how does it come out? And a classic model here is to use what's called a dipole source. So you model everything using as if it came from a source that's sort of buried under the surface. And then you sort of account for some of the stuff that escaped the surface by using a negative copy of that source that's above the surface, and add these guys up on the surface. And you get this kind of pattern of light dying off as a function of distance that fits experiment pretty well. So here's an example using that same marble cube that I showed before. This is the experimental data, so like the light escaping as a function of distance from where it went in. And then if you fit this model to it, it doesn't fit perfectly right near the source, but it fits pretty well. And it makes a decent model for rendering.
Sorry, I have a question.
So
By distance, are we saying that like, okay, the light like got to the surface, and then how, like, what the direction of the distance? Is it like up, like down, or is it going
So this
same
is
direction?
just strictly distance measured across the surface. So
Up
it's
on the
it's
surface?
basically forgetting everything that's actually happening down there in the subsurface and just directly modeling. If light went in here, how much am I going to see coming out at a certain distance
Oh, I see.
away? So it's really like very literally like just take the pixels of that photo and put them on the x-axis of the plot. so if you take if you have a simple model like this, you can use it in a renderer to essentially collect light that's falling on your surface and weight it by the distance that it traveled, and make some renderings. So here's that diffuse glass of milk. If you use this model to make a rendering, you can get something that looks much more translucent. You can see that there's light bleeding into the shadow area where it used to be completely dark, or was only illuminated by indirect reflection from the table. And we were even able to get we made measurements of actually bowls of different kinds of milk using that same apparatus to get different parameters for different materials, and you can render the difference between different types of milk even here. In the interest of full disclosure, I have to admit that the little bubbles that make it look so realistic are actually a ray tracing bug that caused little glitches along the edge there. But it's funny that they look like bubbles. So we also tried this for skin. This is a horrendous looking image now. It seemed very realistic at the time. But it shows how you get this characteristic look of surface reflections, sort of the specular reflection remains sort of detailed and shows the surface structure, where the subsurface kind of spreads out, and you don't see the surface details in the subsurface in the colored reflection. And there's been a lot of work after this on making this into like a real actual model for skin that works for real skin with real parameters and a range of different types. One of the initial impacts of this work was actually just a year later after this was introduced. The visual effects team at Weta Digital was working on Gollum and needed to get him to look like he's been sitting in a cave for a few thousand years. And it turned out for them that translucency was really key to getting the look that they wanted for this very pale creature. This film was one of the first that used it, but it's gone on to become kind of part of the toolbox for rendering skin and other translucent materials in a whole, in most films today. And I guess there's been lots of improvements to this model. Nobody really uses this original dipole anymore.
May I ask a question?
Sure.
So you mentioned that you didn't use path tracer in order to determine how the light spreads through the surface. Because at the time, I'm sure it's probably incredibly computationally demanding. But your model basically fits the scattering expectation that you had. So what kind of tricks did you use in order to get that curve correct?
Well, so at the time, the situation was that you could use path tracing running all night to produce like a reference image to compare something to. And then we did do that. So we could like render a path traced image of a marble cube and compare it to the model. I guess the key that makes this, fast and practical is to basically mine kind of the mathematical physics literature to find all this stuff about diffusion and modeling multiple scattering and find analytical solutions. So like in computer science, we're used to saying like, oh no, we don't want analytical solutions to our problems. We're just going to use numerical computation. But this was a case where importing analytical solutions from the physics literature, or the medical physics literature particularly, where they're very good at coming up with like a simplified model that is a good approximation for a particular phenomenon in a particular kind of range of conditions. And we were able to find ones that worked well for translucent materials, so that you can just directly have some approximation that gives you like a simple formula that you evaluate that just says, if I'm 5 millimeters away from the point where the light came in, how much light is going to end up here. So it's those analytical solutions that make it, the key to making these early translucency models fast. As time has gone on, computers have gotten faster, and more production rendering in practice uses some amount of subsurface path tracing to render subsurface materials, although the intellectual framework kind of lives on and helps inform the little approximations that make, because it's still pretty expensive to really path trace, say, a character with skin with the real parameters and no cheats. And so some cheats about like how you approximate how the light interacts with the surface and things to make it faster are still there. But yeah, but this original dipole model is now sort of the bad old model.
All right. Thank you.
And any other questions about this one? So another relatively old topic, although one that I've been actively working on up until the current time, is the optics of hair fibers. And this is another case where it's a material that sort of defies the standard idea of light reflecting at a surface, and is really important for characters in films. And we started with observations of a couple of features of hair appearance. Or actually, maybe I should back up even and say we started with suggestions from some colleagues who had pointed out that there's a literature in the cosmetics industry on light reflection from hair, and we should mine that literature to try to get better models for computer graphics. So that was kind of the research plan at the beginning. But some of the phenomena that I guess maybe we only saw these phenomena because we knew to look for them after reading these cosmetics papers. But one thing that's interesting on hair that is not absolutely completely black, so even very dark brown hair will show this effect, is that you can see on fibers, you can see white highlights. Whoops. Sorry, I'm going out of order of my slide. So on the basic effect that you see on all fibers is that you see a highlight on fibers, and this highlight occurs roughly it occurs when the light and the viewer are positioned in a particularly symmetric way. And the simple explanation for this is that hairs are kind of like reflective cylinders. So you have a long cylinder, all the surface normals of that cylinder are perpendicular to the axis. And if light comes in, a bunch of parallel rays come in, these different rays encounter different normals, but the normals are all in that plane perpendicular. And each of these rays reflects across that normal. But what you end up with when this happens is all the rays going out have the same inclination to that perpendicular plane as the ray that came in. And so you have a cone, which people call a specular cone, that's reflected from a fiber. And this is really simple to make a shading model for, and early work, the famous work of Kajia and Kay made a sort of Phong shading-like model on this idea that they used for their early work on fur. But if you look more carefully at hair, one of the things that you can see in hair that allows any kind of internal reflection, even pretty dark, is that you have a primary highlight that is white, but then you have some secondary highlight that comes out on the side that's colored. It's a bit more distinct in hair that's a little bit darker. This turns out to be something that can be explained by the surface structure of hair fibers. So hair is, a complicated structure that's made up of lots of different parts, but it basically has long fibers or long, structures, strong structures in the interior, and then it's covered by these protective scales that are called the cuticle. And so one of the key features of hair that explains part of its appearance is that the cuticle is made out of these cells that overlap, kind of like shingles on a roof, so that they're protecting the interior of the hair, but they also provide a surface normal that is like just a little bit tilted from the average normal of the surface. And an interesting thing happens if you sort of just draw the ray tracing diagram for light that is just in the center plane of a cylindrical hair. So here's in white in gray showing the reflection that you would get from a perfectly smooth cylinder. where light that reflects off the surface or light that goes through and out the other side or reflects internally would all come out at the same angle in a perfect cylinder. But once you tilt these surface normals, you see that you have the surface reflection is sort of pushed in one direction, and the reflection that happens internally off the back surface gets pushed in the other direction. So they end up, light that comes from one source ends up coming out in different directions depending on what path it took. And this gives you the ability to see, to explain, this secondary reflection, that one of them is due to internal reflection and comes out at a little bit different angle. Another thing that you can see in hair that is not perfectly round is that the secondary reflection often is a little bit irregular, or is more irregular than the primary reflection. And it has sort of these glints in it. When the glints are kind of dependent on angle. So here's some hair that is illuminated from behind, sort of with the light source behind the camera, and then the exact same hair illuminated with the light maybe 90 degrees away. And you can see at this angle, you get this very strong irregularity. And we made some measurements of this effect, where if you take a hair and you rotate it, illuminating it from one side and measuring the light that comes out, each of these little diagrams here is sort of a polar plot of light exiting the hair. You find that hair comes out in these sharp peaks in directions that depend on how you orient it. And this is something that we genuinely initially assumed was an error in the lab, that we must be measuring like some stray light or something, because how could there be these bright glints showing up all over the place? But once we really did the whole measurement, we realized that there's a pattern to them, and that kind of makes sense. And you can explain this pattern pretty well by ray tracing the cross section of a hair. So if you assume that it's elliptical, then you get the same sort of pattern of reflection off the surface, like transmission through, reflection off the interior surface. And these rays come out in different directions, but the fiber kind of acts like a lens, and it causes them to focus in some directions and spread out in other directions. And it's when a bunch of rays focus into the same outgoing direction that you get these strong glints. And if you work with this diagram here and make models of it, you can kind of explain when those glints are going to happen. So to make a long story short, we built a model based on this, and that was picked up. Again, Weta Digital was one of the first places to pick it up, and one of the first films that actually used this was this their first King Kong? I think this was their first King Kong movie, where they found that it was the key to getting the apes to look correct. And that was like, of course, the fur was a big deal in that film. But it's since been picked up as a model for all kinds of hair and fur that has become kind of the standard thing. And again, it's been extended and improved and corrected in many ways. But this basic structure of thinking of a hair as being kind of like this refractive cylinder that has some cross-sectional shape, where the key properties are sort of what is the surface roughness, what's the tilt of those scales on the surface, and what's the color of the pigment in the interior. Those are that basic idea of how you model the appearance of hair has stuck around. So here are some images from a paper that some people at Disney wrote some years later about the particular implementation of this model that they used there. And this is a little bit later one that also from Disney that shows a kind of later refinement of this model that actually keeps track not just of what direction the light leaves the hair, but where it leaves the hair fiber. And it's always interesting with applications in the film industry that mostly the studios don't want to tell you what they're doing. And so you have to kind of guess or hear through the rumor mill or from informal discussions that they're actually using your model. But it's rare, like in these papers, that they actually publish something saying, this is what we did. We used this model, so that we can say, yes, they really did. But informally, this model and its successors has become a pretty standard thing, both in offline and real-time rendering for hair and fur.
So you're telling me studios can use your work without you knowing it?
Yeah, so I guess that they can implement whatever they want. So we haven't put patent protections in place or anything that would stop them from doing this. Mainly because this would just decrease the impact of the research. And so, yeah, we try to talk them into using the work, but then we don't always know whether they actually did. Although usually we do kind of know because we talk to the people who do it, but it usually comes with oh, but you can't actually like publicly claim that we're using this because it's not something that the studio really wants to say.
Okay.
Okay, but so that was another example of sort of this general pattern of trying to look at why some particular material looks the way that it does, and build that into a model for how to render it. So cloth is another material where it's just difficult to render. It's a material that I think of it, this is sort of one of those computer graphics problems that just keeps on giving because you keep trying to solve it and all you can do is like solve little pieces of it. And cloth is really difficult to render partly because it refuses to have a surface-like structure, right? It's not a surface at all. It's just like a bunch of fibers that are woven or knitted together. And also because it has really complicated structures that people use all kinds of different patterns for weaving and knitting, and it leads to all kinds of different optical effects. And because the material is pretty structured, like it's not very random, it has a lot of order to it. It can produce a lot of effects that are kind of tricky to model. So I want to show you some of the early work in this area that we did looking at kind of a range of different kinds of fabrics, trying to understand sort of why do they look the way they do. They have a certain texture, but they also have a certain a certain angular pattern of reflection, like how do they look, the different colors from different directions. If you've tried to draw or photograph cloth, you may notice that it annoyingly refuses to stay the same color under different lighting conditions, and it's often a little bit tricky to pin down like what color is it really, because it has this sort of constantly shifting color and texture depending on the direction of the light and the viewer. And so we had in some previous work built models that were based on volumes that are able to sort of take a three-dimensional volumetric map of fiber directions. We're calling these microflake models, and could render images of things that are like fabric, if you can give it a three-dimensional volume that says, okay, at each point in the volume, how dense are the fibers here, and which way are they oriented? So we had a simple idea. This was because of some other work we'd been doing, measuring bird feathers, of using micro CT scanning. This was something that at the time I had only just learned about. So this is a technology that is now quite widely available in academic and industry labs. And it's basically the same as CT, computed tomography scanning, that's used in medicine. So it's based on a bunch of X-ray projections through an object, and then a computational process that reconstructs the 3D structure. But it's micro CT because it operates at a smaller scale. So you're able to make reconstructions with voxels that are measured in microns. But mathematically, it's basically the same as medical CT. So we went and CT scanned some fabrics, and I just want to show some slice movies here. So by slice movie, I mean I have a 3D volume where at every point I have a density value that says how much material is here, and then I'm going to show slices sort of as a movie going through here. So let me this lay here. So this is, hopefully the video comes across okay. So this is slices through a velvet material. So here we're starting at the top, where you're looking at the tops of a bunch of fibers that are sticking up. And then you see as you slice down that these fibers are kind of resolving into the yarns that they came from. And then the yarns are actually woven together in the body of the material or in the back of the material. And then there's a 3D visualization on the right there that kind of, not a very clear one, but it shows you what's going on in 3D. And then for a very different material, here's a silk satin. So this is a material. So silk is the fiber and satin is the weave structure. And this is a really shiny, smooth material. And you can see what's happening as we slice again from the front to the back, that on the front surface, we have lots of yarns that are kind of all going in the same direction, and then they interlace together in the back. And this lots of yarns all going in the same direction is sort of what makes it a shiny looking material on the surface. So these two materials have very different appearances. And we wanted to see, can we render the two of them just using this CT data, basically just say like, okay, from this data, we extract an orientation volume and a density volume. So the orientation volume, we ran some filters over there to sort of detect the orientation of the fibers. So you get a map that says, you know, which way are fibers going at each point. And then the CT scanner basically gives you a density volume. That's what it does. So we already have that. And so from these two volumes, we can put them into this volume rendering system and use a scattering model that is, you know, sort of appropriate to some kind of fiber. One of the problems is we don't know how to set the appearance or the parameters of this model that says like, how do the fibers scatter light? Because the CT scanner doesn't tell you anything about how it looks. It just tells you about the structure. And so we did this by solving an inverse rendering problem where we have a rendering of a material, and then we have just a photo of roughly the same shape, and then we match some really simple statistics like the mean and variance of the pixels to get the basically the color and the strength of the specular highlight correct. So based on just this one calibration process, then we can make complete renderings by using the parameters that we find in the renderer.
I have a question.
So here's a rendering of that silk satin material. So this is some years later, so we are able to use brute force. So this is just a path tracing of that volume. At the time, it took 470 core hours to make one frame of this sequence. If you zoom in, you can see that the weave structure is there. But all of the structure of the image, the specular highlights, the sort of shiny appearance, it's not coded into the material model in the renderer at all. It's just emerging from the structure as measured of this fiber material. So here's a little movie that just shows how the highlights behave, so you get a sense for what the material looks like. Okay, so then using exactly the same model, or exactly the same shading model, but with a different volume model, like a different volume that has different direction and density map in it, we can render the velvet material instead. And so here, if you look at the edge of the material, you can see that volume, and this material has some thickness. It's not just a surface with a texture map on it. Oops, I don't have a movie for this one. And it shows maybe the characteristic feature of velvet that you would notice if you're trying to draw or paint this, that it has this sort of bright reflection at grazing angles, so that the edges of things tend to look bright. And again, this is really, the reason this happens is because velvet has lots of fibers that stick up from the surface, and this volume technique just kind of captures that automatically and you know, makes it look like velvet without having to make some model for how velvet looks.
I have a question for you.
Mhm.
Yeah, so you CT scan like this like patch of cloth, and then when you CT scan, it give you the volume of like that cloth, right? So once you have that, like you need to, like, for each of these point in volume, we need to have like some color to basically to render it. And
Mhm.
you say you get the colors from by inverse rendering. So from your image, so when you inverse render, you get the color. So how do you see it, like for each point in density of like this volume? How do you see the color for each of them?
I see, I see. So we basically have the assumption that the fibers are all the same.
Ah,
And so you just have one color. So there's one set of parameters that applies everywhere, that describes both the color and kind of the, I don't know, the tightness of the specular lobes. I mean, like a roughness, I guess, of the fibers.
I see.
Um,
I see.
but there's only one set of parameters. So basically there's like 2 or 3 numbers that come from that inverse rendering process that then describe all the fibers in the material.
I see.
Yeah.
And maybe another question, like another actual question, is
Uh-huh.
when you volume scan this thing, do you get like points or do you get some fiber?
So the output of the CT scan is a voxel grid. So it's basically a great big 3-dimensional array of density values. So there are no points, there are no fibers, there are no surfaces, it's just a volume. And some later work that we did actually did fit fibers to the volume, like sort of turn it into a volume of fibers that you could render using like a hair model. But this work that we're looking at here is just rendering that as a volume using volume rendering. So like rays go into the volume and they sort of march along and they do evaluations of density and scattering properties at each point as they go through.
I see.
And this is part of why they're so slow. Yeah.
Thank you.
One more question.
Mhm.
So you mentioned on the inverse rendering that you got the specularity of the object at different points, right?
Yeah, or at least you get one specularity value by matching the appearance over the whole thing.
Okay, so basically you get the specularity for different lighting situations. For example, if it's lit from behind, as it looks like on this velvet material,
Mhm.
then you get a certain specularity, and the different folds of the clothes, each of them would have some changing levels, right?
So the changing amount of light that reflects specularly to the camera has to do with the geometry of the situation, sort of like what fibers are behind that pixel, how they're oriented, how the light is falling on them, and how they reflect light. But the fibers all have the same property in this model. So the fact that some of them reflect brightly and some of them don't is just because some of them are positioned appropriately to reflect brightly and some of them aren't. Yeah.
So by using the inverse rendering, what do you get instead?
So from the inverse rendering process just basically tells us the color, like the diffuse color of the fibers. And I think it's been a while now, but I think there must be a roughness of the individual fibers that basically just says how to what extent are they kind of mirror-like versus a little bit rough. But most of the shaping of the highlight here comes from the arrangement of fibers in the volume rather than from the properties of the fibers themselves.
Okay, I got that.
In this case, in these particular materials, probably the velvet fibers are actually smoother than the silk ones, even though the silk as an overall material is shiny. Because the velvet, I think this is like an acrylic velvet, so they're probably very, very smooth, circular kinds of artificial fibers.
Okay.
So we went on from this to do some work where we worked with materials that have multiple colored yarns in them and many different kinds of weave patterns, so that we were able to take a complicated weave pattern you would use to make a particular cloth, and we could make a rendering that matches the appearance of this cloth pretty well. Although you might notice here that the rendering, the one criticism, or maybe one criticism of the rendering, is that it's the fabric lies perfectly flat in the rendering, where the real fabric, like the weave pattern, affects its shape a little bit. But as far as the optical appearance, it's matching pretty nicely. And here are some fun renderings we made from this project that are showing. This is kind of a fun example because this is a material that has only one kind of yarn in it. like all of the pattern just comes from changing the weave pattern. So basically there are two satin patterns here that are, you know, oriented different ways. And if you zoom in on this, you see the structure of the weaves. And then here's another example of a fabric that has some kind of nice subtle color changing effects that are caused by using a couple different weave patterns for the different areas of the design. And if you zoom in on it, you can see that there's a satin pattern in some areas and a twill pattern that produces these diagonals in some other areas. And again, these kind of the detailed texture and also these kind of subtle color changes are what make rendering cloth just hard to really get right. And so the high level idea of this project was just, let's see if we can completely brute force the whole thing, and we're just going to actually measure the structure of the material. I think the impact this has had on the film industry is a little bit more in kind of showing the way than in producing models that are directly used. But there are a lot of people who are, I think partly because of seeing this work, have been trying more and more to actually, when they have cloth on a hero character, especially if it's somewhat coarse, really actually model the structure of the cloth and the yarns and get a really realistic appearance that way. Cool. So I think I'll end there since I'm running short on time, and I'll emphasize that, of course, that this is the work of lots of students who are the ones that actually did this work. Sorry, and all the collaborators and funders that helped make this possible. And I can take more questions if there are.
Okay, we can take some questions now from everyone. So please ask any questions you have.
Can you guys hear me?
Yep.
Okay. So when you were talking about translucent materials, so you say that you actually preferred numerical solutions rather than analytical solutions. So is the reason because numerical solutions are scalable, or what is the exact reason that numerical solutions are preferable?
Well, I guess I was saying that that's our habit as computer scientists to prefer numerical solutions. And I guess usually the argument is that because they're more flexible, that in order to get an analytic solution to some physics problem, you very often have to make some strong assumptions about strong simplifications. So like in the case of the skin example, or a translucent material example, the analytical solution actually only works for a flat surface that has an infinite volume of material below it. And that's what the solution is actually for. And then a lot of the trickiness of using this in a renderer, or sort of turning this into a rendering model, is figuring out how you're going to adapt this to the case where, of course, things are not flat, and things are not homogeneous, and all of this. So but the strength of that model is that it gives you a simple expression that you can evaluate it super fast. On the other hand, if you have a numerical solution, like say a path tracer, that doesn't have to make those assumptions, like it can work for any geometry, it can work for inhomogeneous materials. It's great. It works in all cases. It can predict the answer under lots of conditions. The downside in this case is that it's super expensive, and produces some error if it's a Monte Carlo path tracer, it produces error in the form of noise, and so you get a noisy answer that costs a lot to render. But if you have the time to wait for the noise to go away, then you get a nice result that is not dependent on having a particular structure.
Yeah. Okay, I got it. Thank you.
But I think that project was an example of sort of the counter to the usual idea that we always want, that we're never able to really use new analytical solutions that well. That in this case, getting an analytical approximation that is good enough for this one particular phenomenon is a pretty powerful thing for making efficient renderings. even though as you want to make the rendering more and more and more accurate, you might start ditching more and more pieces of that analytical solution and replacing them with numerical things.
Okay, appreciate
Okay,
it.
so as a question, you mentioned that analytical solutions are generally faster and more efficient, but it requires a lot of scientific study and a lot of work before you even go to the rendering stage. And the methods you've mentioned are really like groundbreaking and hard to come by. So as a general question, like how do you usually approach problems like this? For example, like the CT scanning fabrics in order to find out the orientation and density volumes.
Mhm.
And then I would like to know like the approach you have to these kinds of problems in order to find the solutions that are, as you would say, out of the book.
Right. Yeah, I think that the cloth example is one that came from a pattern that is sometimes useful, which is to say, like, okay, I have this problem that I want to solve. You're always in graphics or in any kind of simulation activity, you're trying to balance, like, okay, if I want the cloth model that the film industry is really going to use, it needs to look really good, it needs to be easy to use, it also needs to be fast. And often in research you can make an interesting step by ditching one of the constraints. And so in this case we said, okay, we're going to just do the total brute force thing and forget about whether it's actually practical or not. What if we were to actually just say, no approximations, we're just going to path trace the structure of the fabric? What could we get that way? And so he sort of set off in that direction to say, like, okay, this is a weird thing to try to do because who's really going to, make micron scale models of their cloth, but let's see what we get. And that actually the same thing underlaid some other work on cloth that's more on the animation side that I didn't talk about here, but that is doing a simulation of cloth at the yarn level. And we started that off because we were trying to do simulation of cloth at the sheet level, which is sort of the obvious place to do it efficiently. And we were trying to build better sheet models by thinking about how yarns interact. And at some point we had, this is when I was working with Doug James and John Keldor, and John had spent like a year building a simulator that was able to simulate like a little patch of yarns interacting that we thought we were going to use to make a model that you would use for sheets. But the SIGGRAPH deadline was coming. And so we said, okay, well, what do we actually have? We have a simulator for yarns. So like, what would happen if we just said, forget about how slow it is, we're going to actually just simulate the whole cloth by simulating yarns. And so John was able to sort of scale his simulator up, and we were able to make a bunch of nice results that way, and actually found out some interesting things that changed people's ideas about how to simulate cloth. So those were two examples of taking the approach of, let's take one of the constraints that we usually think of as, immovable, and just throw it away and do something totally impractical and see what happens. And maybe it turns out to be more practical than you thought. I guess the other two projects here were a little bit more in the vein of, sort of trying to look at the phenomenon and understand, just to ask, like, what is the physics behind this? Like, why is this phenomenon happening? What would you like to model if you could? And then go look for other fields where people are modeling similar things. So like in the case of the translucent materials, you find work in atmospheric physics, work in medical physics that is trying to deal with these multiple scattering problems. And lo and behold, they have developed some models years ago that you could repurpose. The hair model, surprisingly enough, it's actually another atmospheric physics thing, but models for refraction through ice crystals in the atmosphere or in ice and snow turns out to end up solving some of the same problems that you need for hair. And we were able to steal a few like really clever geometric ideas from there that let us simplify the model. So hunting for other fields where they're solving similar problems is another interesting approach. It can be difficult because the problem is you have to learn how to read the papers in this other field, which are, written under a different set of assumptions. And that sometimes forms a handy barrier that keeps other researchers from all doing the same thing that you are, because they're not crazy enough to try to figure out how to read these weird papers from some completely different field. But that kind of import of solutions, because you can almost always, with physical modeling, I mean, because you can match the problem across different scenarios and different scales and all of this, you can often find people solving a very similar problem in a very different field. Because another example is more recent work on hair that I also didn't talk about here, that has used wave scattering as the model for how light reflects instead of ray scattering. And this turns out to be basically the same problem, or very related problem to modeling antennas for radios. And so we actually found, actually ended up finding a collaborator by looking at some old papers on antenna simulation and finding the people that had done that, and then talking to them about how we could adapt this for hair simulation, where you're basically just taking the whole problem and scaling it way down to a smaller scale.
That's very insightful. Thank you.
Mm.
Any other questions, you guys?
I can ask one question, maybe
Mhm.
general. And also, I think I should mention from the introduction, maybe Joshua mentioned, he left out that Steve is the director of graduate studies in our department. So if you have any question, he might answer to you about that. But that's not the question. The question is, so for people who want to go to computer graphics, most of the things we are scared of the physics and the maths behind it. Or at least that's me when I first started doing that in my first PhD. And what's your suggestion for people who are afraid of getting involved in graphics because of that?
That's an interesting question. I guess I would say that for many people, and for me particularly or specifically, I think computer graphics is a great vehicle for learning math and physics, because it is, if you think, if you're sort of a concrete and visual thinker and you like to make models and pictures of the things you're trying to learn, then computer graphics is exactly the field where that's your mission, is to make pictures of the thing that you're trying to learn about. And so, like, I certainly had the experience as an undergraduate and young graduate student that many graphics students have, I think, of basically learning linear algebra through doing computer graphics, because it uses linear algebra in such a nice geometric, concrete way that it's a great way to get a sense for, like, what are matrix transformations and what are null spaces and what does the SVD really mean and all these things, because in the applications that you use them for in graphics are just so concrete, and like everything is in a three-dimensional space, or at least like there's an example in a three-dimensional space for everything. And if you're a geometric kind of thinker, then that really helps. And I guess the same for physics, that it actually building simulators and playing with them is a great way to get an intuition for and a sort of an understanding of how models for physics work, because you can really see them. You can see them work, and you can look at what parts of the state space it's going to and why and how it behaves and where it's difficult and where it's easy, and all of this just happens from playing with your code. And it's very different from actually studying physics, say, where you might spend a lot more time trying to analyze, trying to find analytic solutions, trying to find the right approximation or whatever. In graphics, it's more like if you can build a simulator for the phenomenon, then you've won the game. So it's a little bit different that way.
Thanks.
There are other questions? Okay, so if you don't mind asking a personal question,
Sure.
so I've also asked this to Gametru, but like for those of us interested in joining computer graphics and in general, just uh, taking the next step in this field,
Mhm.
I would like to know what are the. So you mentioned that we need sort of a modeling sort of mindset, building
Mhm.
simulators, understanding the linear algebra and physics behind it. But apart from that, what do we need? For example, what should be the next step we take? The people we're supposed to talk to, programs we should look out for, and
Mhm.
in general, the best places to get all of this knowledge and information. Because I'm hugely interested in this field, and I'd like to pick your mind on it.
Mhm. So one of the cool things about graphics is that there's a big community of people who are doing it for fun,
Yeah.
much more so than in a lot of other fields. And getting involved in graphics through actually doing, say, modeling and animation projects is something that can let you learn a lot, especially uh, if you sort of keep thinking about how your tool is working as well as just how to make it work. Because really, like for instance, if you take Blender, for instance, if you're doing animation and modeling, you can learn how to use it by watching a bunch of YouTube tutorials that sort of show you how to get various kinds of things to happen. But you can learn a lot about computer graphics by like just trying to understand and fiddle with it to understand, like once you know how to like build a particular model, like try to understand what all the steps were doing and like what, why did you have to set the transformations the way you did, or like why did it work better to use a loft instead of a revolve to build this or something like this. Why does this work so nicely when I build it with splines where it doesn't work with triangles, and then in some other case it works much better with triangles. Um, the Answering these questions that you run into when actually doing stuff with computer graphics really gets you into a lot of the fundamental questions of how things work. And you can find like a huge slice of all the technology that's been developed in computer graphics in these, like in an open source tool like Blender or Cycles. And it's just cool that the whole technology is there to play with.
And in terms of, for example, continuing your education in that field, are
Mhm.
there specific programs that we should look out for, or you have any insights on how we should apply?
So I guess there are a couple different questions there. So different kinds of programs. So there are PhD programs that you can go to learn how to do research in computer graphics. Um, there are master's programs that are often designed a little bit more around teaching you how to do computer graphics, or how to, uh, how to be, how to do modeling, how to be a technical director or animator or other kinds of roles in film industry and game industry and other graphics heavy jobs. Um, and the programs tend to be in different universities. I'm not a real expert on what they all are. So there are some programs that are really more art programs that are the places that train animators. And that's really very much like taking people who are strong artists and helping them build the sort of technical skills and understanding of how computer graphics works from that side to be effective at making characters and animating them. I guess a lot of the ones that are more from the technical side tend to be a little bit more game focused. So there are a few master's programs that are focused on sort of, how do you get the right training to become a developer for the game industry? Where this may be a lot about coming to understand graphics APIs and the structure of games and game engines, and I mean, games are interesting because they actually explore a pretty broad cross-section of computer science techniques. They're not really just graphics, because you have networking, you have, you know, distributed computing, you have AI, all kinds of things going on. And as far as how to like prepare an application for all these things, I think for most of these cases, I mean, awesome portfolio work, which is something that you can do in graphics more easily than in some other fields, is always a plus. Because not everybody has this, and it's something that stands out. I mean, the standard parts of a graduate application are also there, sort of, you know, the grades and the letters. Doing very cool portfolio projects is also a way, especially if you have somebody locally that you can work with, or that you can show these to over a period of time, or, you know, get them involved in seeing your progress, that they can learn something about how you work from that would let them write a good letter. So I guess my knowledge of how the admissions process works is really more limited to PhD programs, because that's where I hang out. But there, the keys are, there's sort of a baseline of having a strong academic foundation, having good grades, having the right, you know, the right training, so that you know, a graduate program could admit you and not worry that you won't be able to do the work. But then the like standing out is often through some kind of recommendation letters that come from someone who worked with you, where the problem is not so much, you know, them saying this student is the best student ever, but them like making a convincing argument that the student is very strong. And for that, they need evidence, and for evidence, they need to actually know you. And so that's kind of one of the, you know, having some kind of people who are in the right position to write recommendations, which often means faculty at universities who actually know you and know your work, and can say something about it, is really helpful.
Yeah, okay. Thank you so much.
I think we should also, I think we are over time almost.
Yeah.
And just to mention, like for a question, there is also like Monday we have a panel discussion of industries and like researchers and who are like doing this, going through the process. So you can also ask there as well.
Okay.
Cool. All right. Well, this was fun. Thanks for inviting me to come virtually, to virtually come and give you guys a talk.
Thank you so much. We had a very good time. Most of the things we took were just mind-blowing and amazing. So thank you again for your time.
Great. All right. Bye-bye.
Bye.
Bye.
It was inspiring. Thank you.
Thank you.
All right, you guys.